Danny is going to expose you to a real Untitled aerodynamics code that is widely used in the world, and allow you the privilege of using it and generating data just like you're a card-carrying aeroelastician, right? So when you interview for your next assignment, whatever that is, you can tell them that you have used Z-Aero. Is that right?
Yeah.
And you will find out what Z-Aero is. It's just the name of the code. And we're going to do the subside version. What version are we going to do?
We're actually going to do, later on in assignment, I'm going to recreate the flutter test we did in the tunnel.
Yeah.
Just to see if you're going to be sending off.
Yeah. Okay. So it'll be the subside version, and so that'll be fun. And we'll see if you get the same answer that Danny got and that we observed in the wind tunnel test, right? So this will be a moment of truth. Let's see. You before, and there'll be a homework assignment, all that. That currently you're working on finding the next term in the Piston Theory expansion. Is that true? And that's going to be, is that due Thursday? What day did we say? Yeah. Thursday? Okay, fine. So you still have lots of time to work that out. But are there any questions about that?
We're doing the extension in terms of the first block.
Well, you can do both. I don't want to hold back your creativity, but I think the request was for in terms of inverse Mach number, and it turns out one reason why that expansion is useful, somewhat, is that it turns out to be an expansion 1 over Mach number squared, right? Which means the series converges much faster as the Mach number increases, right? Because 1 over Mach number squared would be, for Mach 5 would be like 1 over 25, and it's down the noise level, right? Which is smaller than the overall accuracy of the theory anyway. So there's no point in it. But even at a Mach number, I can't remember how low a Mach number I did in that example in the paper, but we can go down to a Mach number like 1.5 or maybe even less. And if you just use 2 terms, you get a pretty decent answer, I think. Of course, the whole thing blows up at Mach 1, right? And expanding in 1 over Mach number when the Mach number is 1 is a fairly poorly convergent series. But 1.5 would be like 1 over 1.5 squared if it was 2.25. And then the next term would be 1 over 1.5 to the 4th power. That's the one you were deflecting. But you're going to include it. And then the next term would be like 1 over 1.5 to the 6th power. And it gets pretty small. One of the, just one thing, you read it in the paper, one of the reasons we're doing it is it's well known that the standard expansion breaks down around a Mach number, magic square root of 2. Remember, there's something magic about square root of 2. But with this expansion, you can go below Mach number of square root of 2 and still get interesting and sensible results. So, any questions about the homework? I know you've probably already completed it, but any questions about it? No, not yet, but maybe Wednesday night or Thursday morning. Maybe questions, right? Okay, I'm available by email usually. Okay, another announcement on Friday. This is not required, but you will be viewed more favorably if you do this. Elaine Oran is going to give a seminar on Friday at 2 o'clock. Excuse me, at 12, and the luncheon is at 11:30. You may not know who she is, but she's famous, and she's been around a long time. She's very young, but about my age. She's been around. No, she's a bit younger than I am, but not much. Anyway, she's been around a long time, and she's done a lot of work. She's an expert in computational mechanics. So she will solve the Navier-Stokes equation using some appropriate code. And just to make it more interesting, she will include chemical reactions. And she also does flows such as ocean flows and things like that, since she was with the Naval Research Lab for many years before going to the University of Maryland, where she's been a professor for maybe 5 years or so. And she's a member of the National Academy, which is a good thing to do. And so she'll be here on Friday, and I encourage you to come and listen to her, and the food's usually okay too, right? But if you have lunch, there's a moral obligation that you stay and hear the seminar. Okay, I mean, there's quid pro quo. Okay. And I think that's all the announcements I want to make about that. So, while we're waiting for Danny on Thursday, I thought today we'd do a couple things. I sent an email to you the other day suggesting you look at the book and look at some of the typical results. And so I thought I would talk about those and what they physically mean. We've been talking a lot about the mathematics. I thought you'd like to see what kind of results if you persevere and actually do the calculations you might get and what it means physically. So let's do that. If I can find the right page. Yeah. Sorry, this is going to be a little smallish. Oh, well, that's not too bad. Okay. So what are we looking at here? We're thinking of, I take an airfoil, and I give it a step change in angle of attack. That means that suddenly goes to an angle of attack, and I hold it there. And then I observe what happens to the pressure distribution on the airfoil as time increases. And it turns out that the magic time is really a non-dimensional time. So we're going to present everything in non-dimensional form, which gives us, I claim, more insight. So S, by tradition, is called the magic time. So it's physical time multiplied by the free stream velocity divided by a typical length scale, which is usually the chord of the airfoil. Okay. Now, there's a duality between time and frequency. And you see that most clearly perhaps in Fourier transforms, right? Remember, if you have a time history and you take a Fourier transform, you can do something which is transformed, which is essentially the same information, but in the frequency domain. Conversely, if I have the transform of something, I can multiply by e to the I omega t and integrate over all frequencies. There's a factor of 1 over 2 pi that floats around. And then you get the same information, but now expressed in the time domain. So particularly for linear systems, non-linear systems have a little more subtlety. But for linear systems, you can either express things in the time domain or the frequency domain, in principle. Okay. Now, most of these codes, this is Z arrow, are written to express the answer in the frequency domain, which, as we discussed, is convenient for things like flutter analysis and, if you believe in power spectra, for gust response as well. But occasionally, you want to do things in the time domain, although it's only occasionally for practicing aeroelasticities. Having said that, we're going to now look at things in the time domain. There have been some calculations in the time domain, and I think they may give you more physical insight. So we're going to look at non-dimensional time, which corresponds to, in the frequency domain, a non-dimensional frequency, right? It's just sort of the upside down. So this is usually called the reduced frequency. Sometimes, not so much in the aerospace literature, but in the civil engineering literature and some other literature, mechanical engineering, is sometimes called the Struhol number. I always meant to look up in Wikipedia or something and find out who the heck Struhol was. I have no idea. But I've been invoking his name all these years. Presumably he was the person who was interested in a non-dimensional frequency. I'm guessing he was a civil engineer, but I don't really know that. Maybe he's an oceanographer. Okay, so we're going to plot things versus non-dimensional time, and we have a non-dimensional characteristic of the airfoil configuration. It's in motion, if you will. It's a step change from zero angle of attack to some angle of attack, call it alpha, right? So this is the angle of attack. And then we're going to look at a non-dimensional pressure distribution. Thank you. So we're going to non-dimensionalize the pressure. Delta P means the pressure from the bottom to the top, right? It's the net pressure across the airflow. We're going to divide by the dynamic pressure. Remember what the dynamic pressure is? It's 1/2 rho infinity times u infinity squared. And because this is a linear system, we're also going to divide by alpha because everything will scale with alpha. If I did 1 degree, I get an answer. If I did 2 degrees, I get the same answer, but twice as big, right? This is the linear system. So by non-dimensionalizing this way, the result basically doesn't depend on alpha, right? Okay, with all that in mind, let's look at the picture now. So here's delta P over Q infinity alpha. And here's X. This is the distance along the chord of the airfoil from 0 to the trailing edge. C is the chord of the airfoil. And we're at this Mach number. We're at a subsonic Mach number. I'll show you the supersonic Mach number in a bit, okay? But this is a high, but still subsonic Mach number. And each of these curves is the pressure distribution at a given time. So this straight line, well, first of all, this straight line is just 4. I'm just, and here's 8, right? I'm just a gritty. But this straight line is S equals 0. At time t equals 0, when I snap this up, the pressure distribution is uniform. Absolutely uniform. Okay? And the pressure, and this delta PQ infinity over alpha is equal to 1 over the Mach number. So 1 over 0.8 is 5, if I did the calculation correctly. So this straight line is 5. And that happens to be the result given by piston theory. So piston theory, when you read the literature, they say, well, you can use that at high Mach numbers, and that's true. But you can also use it at high frequencies, and that's in that paper as well. If the frequency is high enough, we're talking about non-dimensional frequency, right? If the frequency is high enough, piston theory gives you the right answer, okay? And high frequencies, the duality between time and frequencies, high frequencies corresponds to short times. So if I'm doing a transient, the initial transient at even subsonic Mach numbers is described by piston theory. But then as you go on in time, of course, things change. But right at t equals 0, and maybe for a short time thereafter, a short non-dimensional time thereafter, piston theory is the answer. So here's piston theory. There it is, that horizontal line. And then if you go to 8, this is non-dimensional time, so that's a large time. You're almost, but not quite at infinity. In this case, 8 is almost infinity. Okay. Then you get a curve that looks like this, which mathematically is described by this formula. This is the piston theory result. 4 of the Mach number. At time t equals 0, the pressure has a uniform distribution along the chord, and it's given the magnitude of it, non-dimensional pressure is given by 4 of the Mach number. At very large time, it's somewhat more elaborate. It's 4 over 1 minus m squared to the square root, right? That's the magic factor for subsonic flow. And then it's the square root of c minus x over x. Notice that when x equals c, this goes to 0, the trailing edge. That's the Cutter condition. The Cutter condition, which is widely used in subsonic flow, is actually violated. Well, it depends on what you think happens at the trailing edge. Piston theory says it's uniform throughout the chord, and then, of course, drops to 0. So you could say that it's still maybe the Cutter condition. But you see it really when you go to large times, so that the pressure goes to 0 at the trailing edge, but it blows up at x equals 0. But it blows up like the square root of x, or 1 over the square root of x, which if you integrate this with respect to x, gives you a finite value of lift. Isn't that nice? And that value is pretty close to what you measure in a wind tunnel. It's a little high. Because of viscosity effects and because of finite thickness of the airfoil, it's usually a little less than what this formula would provide by way of lift. It's a pretty good approximation. Okay, and then in between, various other things. It's complicated, right? As time evolves, it goes from this uniform, this result, to this result as time moves on. Okay. Well, what happens? Yeah. What happens in supersonic flow? I'm glad you asked. So in supersonic flow, this is 1.2. What happens at 5? It's essentially piston theory. Right? But we'll get to that in a moment. But 1.2, what happens? Well, first of all, at time t equals 0, it's still piston theory. Except now 4 over m is not 4 over 0.8, it's 4 over 1.2. So it's, here's 4, so it's 4 over 1.2, it's a little, whatever that is, it's a little less than 4, right? So it starts off uniform. And then, as time goes on, it changes in complicated ways. But as time gets large enough, in fact, it goes to this. Okay, so here's piston theory. This is at s equals 0, short time. And this is what happens at large time. And note that these aren't, if m is large compared to 1, this is almost 4 over m2. That's why piston theory is good at all times, right? In supersonic flow, if m is larger. And things don't change much, right? I mean, they change somewhat, but not as much as in subsonic flow. And this is a fairly low supersonic Mach number. This is 1.2. But if I were at 5, it wouldn't be very interesting to plot the results, but you could, right? Okay. The other thing is you can show that in subsonic flow, the steady state, strictly speaking, is not reached until s, the non-dimensional time goes to infinity. In fact, it approaches its steady state limit exponentially in time. Whereas in supersonic flow, after a finite time, things don't change anymore. And this is because why? There's a simple physical explanation. It deals with the speed of sound. All right? It deals with the speed of sound. Well, remember what's happening. If I'm sitting on the airfoil, well, first of all, if I'm sitting in the fluid, and the airfoil makes a sudden change, I disturb the fluid. And in the fluid fixed coordinate system, there are perturbation pressures moving at the speed of sound that way and that way, right? But then if I'm sitting on the airfoil, those disturbances look like they're moving this way at u infinity plus the speed of sound. And they don't really move that way if I'm on the airfoil. It looks like they're moving that way too. The other disturbance that are really in the fluid is going that way. But it's moving at u infinity minus the speed of sound, right? But if I wait long enough, it's moving this way, u infinity minus a infinity, relative to the airfoil. If I wait long enough, the disturbance at the leading edge goes off the airfoil. So if I compute the non-dimensional time it takes, well, it's really what? The physical time is the chord length divided by the propagation speed, which is u infinity minus infinity. Even if I non-dimensionalize that, I find that when the Mach number, when the non-dimensional time s is greater than 2 times the Mach number minus 1, nothing more is going to change it, unless I keep moving the airfoil. But if I just move it once and hold it, in finite time, all those disturbances will propagate in the wing fixed coordinate system off the airfoil. And nothing after that will change. Okay? And how do you see that? Well, I'm glad you asked. Here, in the next figure, here I'm applying CL sub alpha. What is CL sub alpha? Well, I'm glad you asked. This is the common notation. This is usually called the lift curve slope. CL is the lift divided by Q infinity times C, right? And of course, the lift is the integral of the pressure over the chord of the airflow, right? And CL alpha is by definition is CL divided by alpha, right? So this is analogous to what we were applying in the previous curve, but now we're plotting the net lift rather than the detailed pressure distribution, right? Because I want to plot that versus time, okay? I now want to plot it versus time for various Mach numbers. Are you still with me? Okay, good. Okay, so here we are. So this is for different Mach numbers. So here's a Mach number 2. If I plotted for a Mach number 5, it would be, virtually just nothing would be changing in time, right? Because it's essentially piston theory at all times, right? But at Mach 2, you see what happens. There's a initial transient, which it takes a while for things to change from piston theory, and that again deals with the propagation speeds. And then it quickly moves up to its final steady state value, and then doesn't change after that. Here's Mach number 1.2. 1.2. Again, it's piston theory at short times, and then goes up here. What happens at Mach 1? Here's Mach 1. At t equals 0, at non-dimensional time 0, there's a finite result. It's not blowing up. Well, it can't be, because at Mach number 1, piston theory is still the right answer at very short times. But if I keep going along in time, this thing just keeps moving up, and it goes to infinity as the time goes to infinity. And by the way, remember how long it took for the transient to last in supersonic flow? Well, it lasts forever when the Mach number is 1. Because, again, remember, this disturbance, which in the fluid is going that way at speed sound A infinity, is going this way on the wing at U infinity minus A infinity. But U infinity minus A infinity at Mach 1 is 0. So that disturbance at Mach 1 created by the motion of the wing or the airflow never gets off the wing. And in some sense, it builds up so that the linear theory breaks down at large time. But at short time, you probably get a decent answer. Or at least you get a finite answer, right? That's better than infinity. And then there's some other results here for subsonic flow. And another result, let's see. Yeah, here's 0. Here's Mach number 0. Mach number 0 here. And it shows that, let's see. Oh, yeah, this is really interesting. See, so let me show you something. Here, let me do a Mach number 0.8, and then I'll make the point. Here's Mach number 0.8, okay? So it goes like this, and then it comes back up and goes to here. Remember it's piston theory at see, is this the right one? Oh no, excuse me, I did the wrong thing. Here's point number 0.8, like this. Goes back up here. Okay, it goes to 5. This lift curve slope predicted by piston theory is 4 over Mach number. So 4 over 0.8 is 5. There it is, 5. Okay. And then Mach number 0.5, here's the result. And at 0.5, it should be, again, be 4 over Mach number, should go to 8. It does. Hey. By the way, the guy who did this never noticed that that's what was happening, but that's okay. But then, at a Mach number 0, here's it goes right here, and it goes down to, actually, you can't tell it, but that's a little above 3, it's really pi. Turns out the magic number is pi. Except this is not really what happens. What really happens is it goes to infinity at Mach number 0. Remember what piston theory says? Initially, the lift curve slope is 4 over the Mach number. When the Mach number is 0, piston theory says it's infinity. And if you really do a calculation of Mach number 0.01, you get a really big answer at t equals 0. But it's hard to do because, the scales and all that stuff. So usually, people who do incompressible flows, Mach number 0, they don't point that out. Like most of them don't know it. But strictly speaking, at short times, the incompressible flow assumption breaks down. Because if you really just do incompressible flow, you miss the singularity. I think that's interesting. Okay. So, these time histories can tell you a lot, I think. But there are not many of these results around. These results are actually fairly ancient. They were due to a guy named Harvey Lomax, who was one of the outstanding aerodynamicists of what was then NACA, N-A-C-A, before it became NASA, and did a lot of really interesting work. Now we can also, there are a few results for simple wings. These results I've just been describing are just for an airflow, right? It's two-dimensional flow. But here's a plot of CL alpha versus S for what? A delta wing with supersonic edges, all A is the aspect ratio, and a rectangular wing. And the rectangular wing is for a couple of different aspect ratios, 2, 5, and so forth. Let me remind you what aspect ratio is. Aspect ratio, which is sometimes called A, sometimes you see it like this, is, let's see if I can get this right. God, I'm blocking on the aspect ratio. It's area over the span squared. Yes.
Over chord?
No, it's got to be span squared over area, right? Yeah. Span squared over area. And so if I had a rectangular wing, this would be, if span is b squared, then area would be b times the chord, right? And that would be b over c. Oh, sorry. This is for rectangular wing. Okay. It's a measure of how long the span is compared to the chord, right? High aspect ratio means large span compared to the chord. So, what do I mean by supersonic edge? I mean that the Mach number is high enough that the Mach lines emanating from the tip all stay within the wing. So let me draw a picture there. We'll do it for a delta wing. So here's X, here's Y, here's a delta wing. So I'm at a Mach number so that these Mach lines coming from the tip all stay within the wing. That means the edges are supersonic. That means no flow ahead of the leading edge is disturbed. There's no disturbance in the flow ahead of the leading edge, right? And in that case, it turns out, you can show this mathematically, that for that high Mach number, the result doesn't depend on the aspect ratio for CL alpha, okay? Now, for a rectangular wing, it does, because if you think about a rectangular wing, there's always going to be, no matter what the Mach number is, there's always going to be some portion coming from the tips of the rectangular wing where the Mach lines are this way are on the wing, but the Mach line the other way is off the wing, right? And so there's always a disturbance off the edge of the wing for a rectangular wing. Thank you. So anyway, here are results at this one Mach number, 1.4. I'm talking about a moderate supersonic Mach number. And the solid lines are for the rectangular wing. Infinity means it's a very large span. It's really the 2D case, right? 5 is still a pretty high aspect ratio in 2. But notice the result isn't terribly sensitive to aspect ratio. And of course, for the delta wing, it's not sensitive at all. The other thing to note is, if you remember in 2D flow, CL alpha varied a lot, particularly if I'm at Mach numbers like 1.4 and so forth. Here, there's relatively little variation with time, right? Well, by the way, I hope this is piston theory. You know, 4 over the Mach number. Let's see, 4 over 1.4. What is that? Pretty close to 3, right? Yeah. So all of these results start out at piston theory, right? And then later on, as time evolves, things change a bit. Okay. So I think that's interesting. Now, having said that, when you go to the literature and you look at papers, almost all the papers will be plotting results in the frequency domain, because that's where the codes are typically written, and those are the codes that are going to be used for flutter analysis and for gust response analysis. So this shows an example. I have a wing, a main wing, and it's presumably a high performance. Thank you. High performance supersonic airplane. This is the horizontal tail, right? And these things are close enough, right? This distance is a small fraction of the chord of either of these surfaces. So there's interference. So when I analyze this, I have to analyze it as a composite system, right? And I have to allow for the fact that there's interference between these two. And let's see, I didn't write down the Mach number. Hopefully it's an original reference. But anyway, so that's the configuration. Over here we're applying lift normalized versus distance. In this case, it's distance x. Where's z? Y is this way, x is this way, z. I don't think there's z. This must be a typo. Must be x. Anyway, we're plotting this versus x, I think, as real part and imaginary part, because it's in the frequency domain, so there's a phase shift. So they're both a real part and an imaginary part. And this is at some reduced frequency. And then there are other results that are available in the literature. I won't dwell on these in detail. But these codes can do a T-tail. This is a vertical tail, and this is a horizontal tail at the top. It turns out T-tails are relatively prone to flutter. At least that's the folklore. Maybe they're prone to flutter because the theory is less reliable in predicting flutter, and therefore you're more likely to encounter it because your mathematical model isn't as good and things will happen that you don't expect. People have also done calculations where you have a wing and then you put a missile on the end of it. Although typically they squash, in the code, they squash the missile to a flat plate, right? Which is a fairly severe approximation. And then over here, this is just some results for experiment. Those are all those dots, and the lines are from a typical Z arrow type code. This is probably actually double lattice rather than Z arrow, but and this is, of course, this is only one example, but if you look at the literature, this is a fairly typical example. It's neither a particularly good agreement between theory and experiment or a particularly bad agreement. There are worse comparisons, if you will, and there are better comparisons in the literature. But there has been a fair amount of work done on measuring the aerodynamic pressures and the lift on oscillating wings. The Europeans seem to like to do this more than the U.S. people. Typically in the U.S., there are a lot of aeroelastic models. They're flutter models. They're designed to create, or gust models, right? These are majorly responsive systems. The Europeans seem to be more prone to oscillating the model in some prescribed motion, measuring the aerodynamic forces, comparing it to the theory, correcting the theory based on the difference between the experiment and theory. They'll fudge a coefficient here or there, and then they'll do a flutter calculation. And they think that's a better way to go. And so when people get together from the two communities, they have a debate about which approaches. I think that's pretty much what I wanted to share with you about that. That was fairly quick, but any questions? No?
the Mach lines.
Yes.
I know there is for a code.
Yes.
It's a real problem when the Mach lines crosses the body.
Yes.
So can you just explain to which conditions it will cross the body?
Oh, I'm saying. Well, let me draw another picture. I'll be a little more precise.
Take a picture.
Yeah, then. So I'm going to draw my airfoil again, my wing. Remember the tangent of the Mach lines is given by, in supersonic flow, m squared minus 1 square rooted, right? So a particularly interesting Mach number you see, and we actually saw it in some of the other results, or almost saw it, would be a Mach number equal to the square root of 2. Because if Mach number is equal to the square root of 2, if I call this beta, then beta, of course, is 1, right? Because this is 2 minus 1. So in that case, the Mach line tangent is 1, therefore the Mach lines are 45 degrees, right? Plus or minus. So I think I can almost draw a 45-degree line. So what these Mach lines tell us is, because the airfoil is moving, including at this point, it's moving everywhere, but this is the furthest point forward, right? This means that the flow is going to be disturbed everywhere within these Mach lines, right? I mean, I could have another point over here, and it would have Mach lines. They'll be parallel to these, of course. So this point will disturb this and this and this. But the point is, this is the most disturbing point, because that's the one which governs the furthest expanse of the fluid that's disturbed by the motion of the wing. So in this case, this is not a supersonic leading edge, right? Because the flow off the wing is disturbed. So when I say I have a supersonic leading edge, I mean I'm raising the Mach number high enough so that this line moves such that it's within the wing itself, and therefore there's no portion of the flow that's disturbed off the wing, but ahead of the trailing edge. Of course, behind the trailing edge, the flow is disturbed, right? But because of supersonic flow, any disturbance that occurs behind the wing propagates in the fluid forward at a speed of sound, but that's slower than the wing is moving, so that disturbance behind the wing never catches up with the wing. So if I'm in a supersonic wing, I don't know anything about, within the framework of this theoretical model, I don't know anything about what's happening behind the wing if I'm on the wing. Is that? Yeah. So supersonic leading edge just means for a given geometry, it's when the Mach number gets high enough that the flow off the wing isn't disturbed ahead of these leading edges of the wing. And it's easiest to see for a delta wing. If you have a more complicated geometry, you have to kind of go along the leading edge and see how the Mach lines go and make sure everything is lined up. For a delta wing, it's easier to explain. That's why I usually draw delta wings. Also, they're easier to draw. My drawing ability is very poor, so I can usually draw a triangle on a good day. Okay. Other questions? Okay. Okay. Let's see, Howard. Yeah, let me start. I want to do two things. Well, yeah, let me start this discussion. What we've done so far, let me just review the thing. What we've done so far, we have used classical linear potential flow aerodynamics. And we talked about subsonic flow, we talked about supersonic flow, we talked about the various formulations which lead eventually to computer codes that someone will kindly provide you. And we've noted from time to time that when the Mach number goes to 1, whether we start from the subsonic side or the supersonic side, we get in trouble. Although, as I just mentioned, if we look at transient flows, if we're looking at short times, everything's okay, even at Mach 1, according to this linear theory. It's only that if you're at Mach 1 and you wait long enough, eventually all those disturbances catch up with you and the theory breaks down. So, in some sense, steady flow is more difficult. Well, that's probably not quite the way to say it. The theory is it actually works better for unsteady flow than for steady flow. I mean, the computations may be more elaborate because you're dealing with complex numbers and, you know, things like that. But the underlying physics that the theoretical model is attempting to describe is actually better described for short-term transient flows for long-term steady state. And so, if you're careful, it depends on which code you have. In fact, we might do this as a year. I think if you put in the right frequency, reduced frequency, make it high enough, and set the Mach number equal to 1, you might actually you'll get an answer, I think. It won't blow up. Whether how good an answer is to get to say.
They have a specific model for Mach 1.
Yeah, they do. That's right. Yeah. Well, there's another thing, and that's a good comment because it leads me on. There is a transonic counterpart to the classical theory. Okay. And we're going to discuss that. Remember what we have in the classical theory. We have the Laplacian.
More simple.
Yeah, Laplacian minus 1 over the speed of sound squared times d dt of u infinity ddx squared operating on phi equals 0. Right? Now I'm going to expand this out a little bit so you'll see. Make a point. Should keep X, Y, and Z in order, right? Yep, sorry. Minus 1 over A infinity squared. Now I have the second derivative of phi with respect to time, and then I have 2 u infinity. The second derivative is a cross derivative plus u infinity squared, second derivative with respect to x. All of that equals 0, right? And as I mentioned, things really, in some sense, get most severe in terms of this theory breaking down for steady flow. So just for the moment, we'll come back to unsteady flow, but just for the moment, let's look at steady flow, which means these terms go away. Right? So now, this term and this term are mathematically alike, right? They're both secondaries with respect to x. And here, this one has a coefficient of 1, and this one has a coefficient of minus u infinity squared over a infinity squared, otherwise known as 1 minus the Mach number squared. Oh, I left out something. It's really important, right? Sorry about that. Now, when the Mach number goes to 1, that term goes away. If I were in 2D flow, that term wouldn't be there either. And I would get a degenerate model and it's just useless. If the flow is highly three-dimensional, so this term is really important compared to this term. That's a low aspect ratio wing, right? Where the chord is large compared to the span, right? What's left is Laplace's equation, but only in the YZ plane. That is actually called something. It's useful. It's called slender wing theory or slender body theory. So this is called slender wing theory. And if you solve that, and for example, that result I showed for a delta wing in the book, you probably actually get a pretty decent answer. Not a perfect answer, but a decent answer. On the other hand, for a very high aspect ratio wing, where this term is not terribly important, and this term goes away, and certainly for a 2D airfoil, the theory just breaks down entirely. Okay, and it's because you have a cancellation of two terms, essentially, right? And if this were a plus sign, aerodynamics would have gone down an entirely different path. So the question is how to correct for that. And what you do is you go back, starting with earth, fire, wind, and water, construct a nonlinear potential flow theory, and then very carefully do a perturbation analysis, allowing for the fact that I need to include the next term. It's a little bit like including the next term in piston theory, right? I have to include the next term. See, what I was arguing, get to construct the classical theory, I was neglecting terms that are small compared to each of these terms, or at least one of them. But because this cancel, the term I neglected can't be small compared to something that's zero, right? Or something that's nearly zero. So the physical effect of that is that the Mach number, this is the free stream Mach number, right? This is the Mach number associated with U infinity over A infinity, is replaced by the local Mach number. What do I mean by the local Mach number? I mean a better approximation to the local flow velocity divided by the local speed of sound. I really need to compute the local speed of sound as well as the local flow velocity to compute the local Mach number. Okay? And that's done in the book. It takes about 5 pages. And I'm going to allow you to read that. Now, if you actually insist, I've got my book with me, I can go through that derivation. But I think I'm just going to tell you that, and tell you what the answer is. And as soon as I find it. As you would expect, the local Mach number squared is equal to the free stream Mach number squared times a factor, which is 1 plus gamma plus 1 times phi x over U infinity. Okay? Now, gamma, what's gamma? Gamma is the ratio of the specific heats. It's 1.4 for air, and that's pretty good. Actually, the people at NASA Langley, when they run the transonic dynamics model, sometimes they use Freon. And I've forgotten, Freon has a different gamma. It's 1.1 or something like that. Yeah. So you have to account for that. What is this? Well, first of all, without that term, it's just classical theory, right? This term is the fluid velocity component in the x direction, right? Divided by the free stream. And really, this thing typically is very small compared to 1. But the reason we retain it is because when the Mach number itself is 1, there's this other 1 that's canceling this term, and therefore I'm going to get 0. So this is small compared to this. This is small compared to a lot of things, but it's not small compared to the difference, which is canceling when the Mach number is very close to 1. Okay? So with this replacement in this equation, that's called transonic small disturbance theory. This is not the full nonlinear theory. The full nonlinear theory is much more elaborate and it's written down in the book. And people have written CFD codes, not so much anymore, but back in the day, to solve the full nonlinear potential flow equations. In fact, when computers were first becoming viable in the mid-'80s, this is probably about 30 years ago, they attacked nonlinear potential flow theory. The hope was that that would be pretty good and a lot better than linear potential flow theory. Turns out it's somewhat better, not a whole lot better. But nevertheless, but Zona, the company that produces Z-Aero, has something called Z-Tran, which is more or less trying to solve this set of equations. Okay. Now, what does this do mathematically? Well, that term, when I multiply by this term, which I almost left out, when I multiply this term by that term, I convert a linear PDE into a nonlinear PDE. So all the usual methods, analytical methods, Green's function, Fourier transforms, Laplace transforms, I don't say that they won't work. I just tell you that no one has ever made them work. So if you can make those work, people say, well, gee, why didn't you do that 50 years ago when we needed it? But you could write a paper, right? But anyway, but what people did early days was they used finite difference methods in spatial variables, probably some harmonic motion in time, or maybe they did a time march. But anyway, so now, having said that, it was really interesting historically. Historically, people looked at this and they immediately went off to the computer and started solving this problem as best they could. But what was not initially recognized was that you can still develop a linear theory that's useful. And how are we going to do that? Well, it's the following. When I have, there's some physics involved and also some mathematics. When I have an airfoil, I'll draw myself a nice airfoil. And I have the oncoming stream. One of the physical characteristics of transonic flow is, whereas in subsonic and supersonic flow, the actual shape of this airfoil doesn't matter very much in terms of generating lift as far as the thickness is concerned. I mean, what I can do is I can usually replace that airfoil with a mean camber chord, which allows for curvature and allows for possible motion. But the actual thickness I can assume is 0 because the thickness, according to linear theory, gives the thickness contribution generates a perturbation pressure that's the same on the top and the bottom, therefore the net is 0, so I can forget about the thickness. But in supersonic flow, that's not true. Excuse me, in transonic flow, that's not true. It's also not true if I put this at a given angle of attack and then oscillate at about that angle of attack. In supersonic and subsonic flow, the lift or other aerodynamic forces through the oscillation itself doesn't really depend on that small angle of attack. But in transonic flow, it does. What really happens is the base, in classical flow, we're basically assuming that the mean flow can be approximated by just U infinity. Right? It's just a nice uniform flow, and we're doing a perturbation about that. In transonic flow, we really need to allow for the fact that the steady flow is changed from the free stream flow by the thickness of the airfoil by any mean angle of attack before we begin to oscillate. So, from a mathematical perspective, that means we need to take phi, or we can take phi, which depends on x, y, z, and t, right? And we can write it as phi, I'll call S for static or steady flow, which only depends on x, y, and z, that's the flow over this before it begins to move, plus a dynamic part, which may depend on T, which takes into account the actual motion. And what I'm going to do is I'm going to construct a linear equation for that. The equation for this will be nonlinear, but a steady flow. And, you know, if you go out into the aerodynamics community, you know, 90-some% of the people out there are doing steady flows and have written code. So why should we bother to write another one? So we know how to compute steady flows more readily than unsteady flows. So the thought is, I'll take a steady flow code, which is nonlinear, in this case nonlinear in context of potential flow theory, and use that, and then do a small perturbation associated with the dynamic part. And then I will end up with a linear equation for this. That's the good news. The more sobering news is, in that linear equation for PD, there will be coefficients which depend on the steady flow solution. And the steady flow solution, unlike uniform free stream flow, which is constant everywhere, that steady flow solution will depend on X, Y, and Z. Did I say that too fast? See, I've done this before, so it made perfect sense to me. Did I say that too? Okay, let's go back and do this. We're going to write down the transonic small disturbance equation. And what is it? It's 1 minus the local Mach number squared times, I'm going to use this notation. It'll save me x means second derivative with respect to x. That's okay? Yeah, fine. Plus phi yy plus phi zz minus 1 over a infinity squared 2 u infinity phi xt plus that's all right. Well, I can do it here. Plus phi tt. There was a phi xx term here, right? But I took it over here. Thank you. And of course, ml squared, right again, m infinity squared 1 plus gamma plus 1 dx over u infinity. Okay? And so, and I'm going to assume that phi is a steady flow plus a dynamic perturbation. So this part, I'm first of all going to solve for when there's no motion of the airflow. So PD is 0, right? And so that's just governed by the steady flow equation. So phi s is 1 minus ml squared phi phi sub s xx phi s yy plus phi s zz equals 0 because these terms are 0 when I'm just computing the steady flow, right? And then of course the local Mach number steady is this. Okay, so I've got to solve this problem. And this is a nonlinear PDE, but it doesn't depend on time. Okay. In fact, in principle, I could, if I were willing to go to the wind tunnel, I could measure the steady flow. Now, it's true that measuring the steady flow everywhere in the flow field might be a bit of a task. But it would be relatively easy to measure the local Mach number on the surface of the wing. And that's been done. And in fact, one of the approximations that were made probably consistent with the overall reliability of this theory is to assume that this phi s that I'm going to use subsequently, I'll just replace it by its value on the surface of the wing. I won't worry about its dependence on Y and Z, right? In fact, you can relate the local Mach number to the steady flow pressure distribution on the wing, which is relatively easy to measure in an experiment. But anyway, somehow I'm going to get a representation of the steady flow, and then when I do this, and I substitute in here, I'm going to get some nonlinear terms. But each time I get a nonlinear term, like, well, I have a nonlinear term like this, right? That's from here to here. That's going to be the nonlinear term, right? What am I going to do with that? I'm going to replace that by phi s xx plus phi d xx times phi sx plus phi d x. Okay. Thank you. And I'm going to ignore the term that involves the product of phi d, right? And I'm going to retain the terms that involve this one times this one and this one times this one, okay? And better than that, when I substitute this in here and make those approximations, I can subtract out this equation, the steady flow equation, and the only thing that will remain are homogeneous terms in phi sub d. But there will be coefficients that involve this and this in the phi sub d equation.
Which one you will take from the steady flow?
Well, but I'm going to, this term I can eliminate by subtracting out this substitute in this and subtracting out from the full equation that now includes phi sub d. I mean, this is standard when you're doing a small perturbation about some non-trivial equilibrium. This happens in a lot of different engineering systems and nonlinear oscillations. So, okay, but the people who, most of the people who are doing transsonic aerodynamics for aerodynamicists, they didn't really understand dynamics for the most part. So this was considered revolutionary a bit. But someone who does dynamics will think, well, of course that's what you do. Right? That's what we always do. I remember I was writing the paper and I finally got published, and one of the reviewers said, well, it's impossible to do that. I said, no, it's not impossible. See, I did it. You know, they're 2 or 3 pages. Anyway, sometimes the culture is such that people will think something's impossible because they've been trained to think in a certain way. And for someone else who's been trained in a different way, for them it's obvious. Maybe they don't understand something else. Okay. Anyway, I think I'll stop there, and then what I'll do next time. Oh no, I'm not going to do it next time because you're going to talk next time. But when we come back to this, I'll write down the linear equation for phi sub d. It will have variable coefficients which depend on the steady flow. And there are actually a couple of simple analytical solutions available which give you qualitative information. But no one does this anymore, unfortunately, because it's been largely superseded by CFD codes that just take the full equations and so forth. Having said that, even in CFD circles now, you can do the same thing I've just described here for the Euler equations and also for the Navier-Stokes equations. And that's useful. So even if you're running the CFD code, what you might do is you would take the CFD code, you would compute the steady flow, Euler or Navier-Stokes, and then you would give it a small perturbation, small motion, such that you're fairly certain that the answer is linear in the motion. That is, the flow field is proportional to the amplitude. The unsteady flow field is proportional to the amplitude of motion. In fact, you could try different amplitudes of motion and see how far out you can go, and everything remains linear in the motion. And then you can use that representation, compute aerodynamic influence coefficients, and do a flutter calculation in the standard way, even though you got the information from Navier-Stokes code. But you don't care. All you have is a plot of CL unsteady versus reduced frequency or something, right? So people have done that, and that's a useful thing to do. So even though this particular model isn't used much anymore, the ideas that emanate from that led to people now doing similar things for these more elaborate CFD codes. Okay, questions before we stop for the day? Okay, so you've been introduced to transonic flow. Introduced. There's a lot more that can be said. Anyway, next time we're going to hear about a real unstable dynamics code, and you'll have the opportunity to put your hands on it, lay your hands